Welcome back to Elementary Statistics. In this video, I want to look at the z-test for two means, or to be more technically correct, we're looking at a two-tailed, two-parameter z-test on means. The z-test itself is far more commonly useful for one-parameter data. The z-test for one parameter relies on knowing the mean and the standard deviation of some known population and then comparing that to the mean of an unknown population. In practice, usually we don't know the mean of any population, and so we have to do work from the beginning. And so the two-parameter test generally is going to be using one sample to estimate the population mean for one group, the control group, and that's going to take the place of a known population. Another sample is going to be estimating the mean of an experimental group, the experimental population, and then we want to compare those two populations. The z-test is very rarely useful in this context because the one thing that you need in order to perform a z-test is some estimate of the standard deviation of the population. That's just as true in the two-parameter case as in the one-parameter case. Knowing the population mean and standard deviation is common when you have a theoretical distribution. When you don't have that, we have to estimate everything, and we're going to develop some more tests that will allow us to do that. But while we're talking about the z-test, and while we have that in mind, I want to walk through and talk about what two-parameter hypothesis tests would look like so that we can extend that out when we get to new and less familiar statistical values. All right, so if I get my head out of the way, let's dive right in with an example. So suppose that a researcher wishes to determine whether there is a difference in the average age of nursing students who enroll in a nursing program at a community college versus those who enroll in a nursing program at a four-year university. Fill in those missing words. So in this case, we're going to use notation with subscripts. Mu1, sigma1, n1, x bar 1 are all data about the nursing students at the community college. Mu2, sigma2, n2, x bar 2 are all data about the nursing students at the university, at the four-year college. And I want to stress in this problem, I'm not interested, the researcher is not interested in analyzing the mean at the community college. The researcher is not interested in analyzing the mean at the four-year university. Researcher is interested in comparing the two populations and determining if they are the same or if they differ. So in this case, the null hypothesis is going to be that the mean age at the community college is equal to the mean age at the four-year university, and the alternative hypothesis is going to be that those means are different in those two populations. All right, so thinking through our steps of hypothesis testing, we've gotten through a good portion of them. We have a question to be answered. is the age of nursing students at a community college different from the age of nursing students at a four-year university? We have a variable and even a statistic that we can analyze, the mean value of the ages of these students. We have a null hypothesis, we have an alternative hypothesis. The next thing up is to determine a level of significance. And we have some options as to what we can choose there. This is a choice, and I'm looking for where I have it written down. As soon as I looked away from the camera, the glare of the light got in my eyes. But let's choose a level of significance of 0.01. So we're looking for 99% confidence, and I'm getting really blurry, aren't I? There we go. All right. Up next, we want to start looking at collecting our data. And so we have some data here. So remember, N1 X bar 1 is the number of students from the community college involved in that sample and the mean age. So we analyzed 32 nursing students at a community college, and their mean age was 29.5. We analyzed 27 nursing students at a four-year university, and their mean age was 22.2. The other piece of information we need are the standard deviations. And this is where you have to be lucky. In our case, I'm going to assume that the students at this community college and the students at this four-year university have had their ages analyzed in a couple of different ways before, so the standard deviations are known. Sigma 1 is 6.8, and sigma 2 is 3.4. All right, so we know the standard deviations of each of these populations. That has to be something we know from the past. Again, our process does not give us enough information to analyze and calculate the standard deviations. Calculating the means is something we can do. Right? If I had raw data about my sample, I could calculate these means. I'm not doing that in this video just because it's not worth the time. You know how to calculate a mean. I trust you are able to do that. But the standard deviations have to be given to us. If we do not have some piece of information that we already have standard deviations for each of these populations, then we cannot proceed using a z-test. We have to use a different kind of test. And we will be talking about other kinds of tests where the standard deviation does not need to be known for the population before we get started. The other thing we need to consider about a two-parameter situation is that we have two things that we are analyzing. And so we need some way of talking about these two different approximations, two different estimates with what would be two different confidence intervals. And coming up with two different confidence intervals and determining whether they overlap is mathematically challenging. So I'm actually going to rearrange my null hypothesis and my alternative hypothesis into a way that's going to be easier to work with. And this is usually going to be what we do whenever we have two parameter data. I'm simply going to subtract on one side. I'm going to write this as mu1 minus mu2. And the null hypothesis, that equation, can equivalently be given as mu1 minus mu2 equals 0. The alternative hypothesis can equivalently be given as mu1 minus mu2 is not equal to 0. And we can estimate this as x bar 1 minus x bar 2. So in this case, that's 29.5 minus 22.2, which comes out at 7.3. All right, so there's our point estimate for the difference between the means. 7.3 is definitely not zero, but point estimates don't have a confidence level. So we need to go onward. If alpha is 0.01, that means we're looking to construct a 99% confidence interval. And we've used these numbers before. By the time you are done with this lesson, you will have memorized the z-score for a 95% confidence level and the z-score for a 99% confidence level. They just show up that often. So our z-scores in question are plus or minus 2.58. And then we need sigma over the square root of n. Well, that's a bit of a problem. We have two values of sigma and we have two values of n, and we need a way of combining them. And the choice we're going to use is going to be the same choice that we used for finding standard deviations in the first place. We're going to take the root mean square. So instead of sigma over n, I'm going to take the square root of sigma 1 over the square root of n1 squared plus sigma 2 over the square root of n2 squared. And yes, those squares and square roots cancel each other out. So we can think of this more simply as sigma 1 squared over n1 plus sigma 2 squared over n2, and then take the square root of all of that. So in our case, sigma 1, it's scrolled off the screen now, but sigma 1 is 6.8, n1 is 32, sigma 2 is 3.4, n2 is 27, and then we want the square root of all of that, which my calculator is happy to tell me is something in the ballpark of 1.37. Now we want to take our estimator, x1 minus x2, plus or minus our z-score, 2.58, times all of this mess. So x1 minus x2 was approximately 7.3. And then 2.58 times 1.37 is something in the ballpark of 3.53. And so our range is, well, 7.3 minus 3.53 is about 3.8. And 7.3 plus 3.53 is something in the ballpark of 10.8. And this is not just one mu, this is our estimator for mu1 minus mu2. 0 is not in this interval. And because 0 is not in this interval, we reject the null hypothesis. So, as I said at the beginning of this video, using the z-test for two-parameter data like this is very rarely something we can do. Having data where we know the standard deviations of two different populations and not their means is incredibly rare. But the rest of the process is something that we're going to be looking at as we move forward. Right? In future videos, I'm going to be looking at different hypothesis tests. One of the ones that's coming up very soon is the t-test, which allows us to look at situations where the standard deviation of the population is not known, but the mean of the population is known. Or in the two-parameter case, we know two means, we know two standard deviations of samples, not populations. But even at that point, the rest of the process is going to be the same. The z-score is going to become something different. The particulars of what's going on here are going to become something different. But the estimator is going to be the same. Whenever you have two population or two parameter data, you're going to be looking at the difference between those values and trying to see if 0 is a reasonable fit. If 0 falls into your confidence interval, then you accept the null hypothesis. If 0 does not fall into your confidence interval, you reject the null hypothesis. As in this case, we've rejected the null hypothesis. That means that there is a statistically significant or a measurable difference in the ages of the nursing students at the community college and the ages of the nursing students at the four-year university. That's all I have on this video. Thanks as always for joining me. I'll see you next time.